Okay, live show. What? The problem.
Mr. Dutt can start.
I am ready. Professor Dattar, I am ready.
Yeah. So, Satya, shall I?
Yeah. Start.
Okay. So, thank you, Satya, for this. I'm supposed to introduce Dr. Nayak. So, let me say a few things. He did his bachelor's in mechanical engineering at the NIT Rourkela and master's at NIT Warangal. PhD from the Tokyo Institute of Technology in 2000. And he did a few postdoctoral at University of Delft, Netherlands, 2002 to 2003, Royal Institute of Technology, Stockholm, 2003-04, and also spent a couple of years at the Institute of Nuclear Energy, Stuttgart, 2007 to 2009. His main areas of work and interest are he has played a key role in the design of the advanced heavy water reactor, particularly its passive safety systems. He has also established facilities to check their design, to finalize their design. Then he has also worked on managing the core melt accidents, which is a very important thing. For instance, it happened in Fukushima. And he's currently working on small modular reactors, which could in principle be placed at vacated coal-based thermal power plants. He has won several awards, including the Homi Bhabha Science and Technology Excellence Award, the DAE SRC Outstanding Investigator Award, and Group Leader Awards for S&T Excellence, and so on. He's the author of 4 books, as well as about a few hundred research papers. Of course, he is a fellow of the Indian National Academy of Engineering and the Maharashtra Academy of Sciences. So today's talk is on, basically how we could hope to reduce the carbon footprint using nuclear reactors. So, Dr. Nayak, the floor is over to you.
First of all, I'm grateful to TIFR for giving me this opportunity to speak on very important theme that how relevant is nuclear energy, especially a new technology called small modular nuclear reactors in the decarbon energy sector. And now I'm also thankful to Dr. Dattar for introducing me to this very, very highly esteemed audience. So, as you all know, that energy is the health of a nation. The nation's health, if we have to calibrate, it is reflected in terms of how much energy per head is consumed. And India has been striving over the years, if you see, especially on this important aspect of enhancing the per capita energy consumption. And that is not only for India, most of the developing nations, even developed nations, the life standard has improved, or it's reflected that it has improved in respect to the how much energy it is consuming. And looking that aspect, it's not only India, most of the developing nations, they have been really striving to increase the per capita energy consumption. And we'll see also down the line, what is our policymakers, the Niti Aayog speaks about how much energy we have to really consume or we have to produce over the years. That is one aspect. The other aspect is, while this journey is going on, there is a sudden break, especially with the reduction, with regard to reduction of the carbon footprint. That is decarbonization of the energy sector. So while there is a break which is coming to decarbonize the energy sector, at the same time, there is a big hunger for India to increase the energy consumption. What is the role of nuclear in this war or in this perspective? That's what I'm going to bring out. And in that perspective, I'm going to speak out how small modular nuclear reactors, which is being developed by most of the developed nations or by most of the nuclear technology holders, how they are going to play a very major role in the next few decades for India. So, there's some problem with my
Sir, in that case,
pages.
you can skip full screen, sir. To come to the regular PowerPoint setup, just skip the
Yes.
full screen.
Yeah, I think the computer is it is a hanged probably.
Oh,
The- Only what I can do. Please bear with me. There is some
yeah,
problem.
it's okay. It's okay. Yeah, the slides are moving now. Dr. Nayak, can you hear me? Yeah, the slides are moving.
So, sorry, there was a problem in the moving of the slides. So before we proceed ahead, let's look at what is the total amount of the primary energy supply in India as on today. Believe it or not, we are one of the largest producers as well as consumers of the energy in the world. We are the third largest producer as well as the third largest consumer of the energy in the world. So today we produce something like close to 900 million tons of oil equivalent as the primary energy supply. And they come primarily from coal, almost 30%, 34%. Oil is another 25%. Natural gas is 6%. Biomass is 13%. Renewables is very small, around 3%. Others, which include nuclear, hydro, and other things, is close to 9%. I don't know. Next slide down. Be here. Let's see.
Yeah, we can see the slides now move.
Now let's look at how much energy we consume in different ways. Sorry. Let's look at the source of distribution of the primary energy supply. Today, if you look at the coal, almost 2/3 is available in India, 1/3 we import. So out of close to 900 million tons of oil equivalent, 261 million tons are available in India, almost 129 we import. Oil is the reverse, 1/3 we have, 2/3 we import. Bioenergy, almost everything is available within the system. Natural gas, 50-50%, in the sense 50% we import and 50% is available within the system. And let's look at how much we consume out of that. Because when you convert the useful sources of energy to usable form. Some fraction is lost. This is the first law of thermodynamics. So something is lost. And out of this 900 billion tons of oil equivalent, when you convert to usable form, almost 600 million tons of oil equivalent is available. And if you look at the industry, residential sector, transport sector, they maximum consume in the sense the largest consumer is the industry sector, then followed by residential sector, transport is almost 17%, service sector is the balance 13% of the total. And this is what is something really we all have to worry about. This is nothing new, but we have to realize it. The topmost graph you see is the total amount of the energy which is consumed by different countries in the world. And China is the largest among in the world, followed by United States. As I said at the beginning, we are the third largest consumer in the world. But we are also a big population, about 1.4 billion population we have today. And that is why our per capita energy consumption is really poor, almost 1,208 kilowatt hour per person. And if I compare with our neighbors, including Thailand, for example, is almost close to 2.5 times of ours. Our neighbor Thailand consumes roughly 3,000 kilowatt hour. Malaysia 4 times. China almost 4 times. Even the world average is almost 3 times of ours. The Western countries or OECD countries, which are developed, we say almost 6 to 7 times. And that is why, if you look at the leftmost graph, our Human Development Index, which I again say from the first slide, that gives a reflection of the amount of energy that we consume per head. And that is reflected in terms of quality of life is relatively poor as compared to the developed nations. And that is where the India has been striving over the years that how to improve our per capita energy consumption. And that is how our HDI has to be closer to the Western world. How much is the energy demand for India? If you look at our policy body, the NITI Aayog speaks out that India houses today nearly 100 million people without access to electricity, and a large fraction of people, almost 830 million people, without access to clean cooking fuels. In fact, the recent report from Indian Energy Agency has given such a remark that large fraction of Indian villages and African villages, they still use cow dung as the cooking fuel. This is really a bad remark with regard to the greenhouse gas emission, because we have been consuming the cow dung as a cooking fuel. Of course, our total installed capacity for electricity generation has increased continuously. Really, if you look at quite a good amount, almost 8.42% per year. But this is mostly driven by our economic growth, which is one of the fastest in the world. And as I said, we are the second largest consumer market in the world. But we have an evil is the population. And today our population is 1.4 billion. And it is estimated that another 30 crores are going to join us in the next 2 to 3 decades. Believe it or not, another 30 crore people are waiting to join us in the next 2 to 3 decades. So then we'll be one of the largest populous country in the world. And to meet this electricity demand over the next 20 years is not far away, it's just 2 decades, we will be requiring the size of electricity of the European Union to what it is now. So believe it or not, this is the biggest problem. We will be requiring an electricity supply system of the European Union in the next 2 decades. And why such a huge demand is going to come for India is all because more people are moving to cities. The urbanization is growing, and is expected to grow something like close to 50% by mid of this century. GDP of India is expected to grow at a CAGR, that's a compound annual growth rate of 8.5% between now and 2047. And there will be also much higher energy demand in the manufacturing sector. Today is almost 16%, likely to grow to 34% by mid of this century. And we have also very ambitious plan in energy sector, provide continuous uninterrupted power supply to every household, housing for all, building several smart cities, a reduction in oil and gas import duties, and so on and so forth. And most important, we have also promised to provide clean cooking fuels to all. So how much energy will be requiring by mid of this century? I'll tell you, this is the most biggest question and most unsolved question today. If you look at the last 10 years, from 2005 to 2020, sorry, in the last 15 years, I have plotted the amount of energy which consumed by India is a straight line, the bottommost line. Let me say it goes very linearly. We have grown from something like close to 5,000 terawatt hour, and today we are just below 10,000 terawatt hour. And if we move in the same straight line, which I say as a business as usual model, by mid of the century, we'll be requiring something like 20,000 terawatt hour. And we say that is very less in the sense we want to have a lifestyle of the Western world. So our energy consumption, our policymakers, everyone, we want that the energy consumed by Indians have to grow by 5 to 7 times. That means by mid of the century, from 10,000 terawatt hour, we should reach something like 50,000 terawatt hour. How much? 10,000 today to something like 50,000 terawatt hour. So 30,000 terawatt hour has to be added to Indian system in the next 30 years. 30 years, 30,000 terawatt hour additional. How big is this question? You will be realizing after a few slides. With the existing 10,000 terawatt hour, which we consume, already there is a bill on the greenhouse gas emission, which is the biggest worry worldwide today. And it's all because, if you remember my second slide, large fraction of the energy we produce primarily from carbon-based sources, coal, oil, and gas. These three, the carbon-based sources. And CO2, carbon monoxide, nitrous oxide, methane, and so on, which I have shown in the rightmost graph. They are the primary sources of the greenhouse gas emission, which primarily are coming from the primary energy supply. So this is already the bill we all have got. And if you look at the last 30 years, from 1990 to 2020, there is very, very significant amount of GHG, which is your greenhouse gases, which has been emitted over the world. It's not only for India. This graph which I'm showing is showing that from 1990 to 2020, how much GHG have been emitted from different sources. And I'm just talking about the total amount. 1990, it is something like 40 gigaton CO2 equivalent per year the world was emitting, which is today roughly 60 gigaton CO2 equivalent per year. Almost 50% it has enhanced or it has increased in the last 30 years. And if you look at this graph, who is emitting how much? We are not that bad. We are the third largest emitter apart from China and the US. Country-wise, I'm speaking out. And we also emit close to 2.5 billion tons of CO2 per year. How much? 2 to 2.5 billion tons of CO2 per year, apart, I think, just behind China, which is the largest emitter, close to 10 billion tons of CO2, and United States is something like 6 billion tons of CO2 per year. And this is the Nobel Prize of this year, which the Japanese professor Shiroku Manabe got for his work on the impact of the CO2 on the greenhouse gas or on the atmospheric temperature. This is the work which he did long back in 1967. All of you might have read it. that influence of the CO2 concentration in the air on the atmospheric temperature. And what it shows that if the atmospheric CO2 concentration increases by 2 times, the Earth's temperature is going to rise by 2 degrees Celsius and vice versa. Please just remember these two words. If the concentration of CO2 increases by 2 times, then the ambient temperature or the Earth's temperature is going to rise by 2 degrees Celsius and vice versa. If the CO2 is reduced by 2 times concentration, the atmospheric temperature is going to reduce also by 2 degrees Celsius. This work he did long ago, 1967, by simple, those days the supercomputers were not available, not rigorous mathematical models, simple hand calculation with some simplified models. He could predict long ago, but it was not accepted. Scientists were not accepting these conclusions. There are belief that water vapor could be the major cause of the greenhouse gas emission or the rise in atmospheric temperature. Until recently, it was really proven that CO2 is the main cause of the atmospheric temperature rise. And how fast we are approaching to double the CO2 concentration in the Earth. Below this number, please remember that if the CO2 concentration increases by 2 times, the Earth's temperature is going to rise by 2 degrees Celsius. Then how fast we are going to reach the 2 times concentration? This graph shows. Already it shows that 50% level we have crossed. From pre-industrial level, it was something like 200 ppm, and today we have reached something like 400 ppm. So 50% rise has happened from pre-industrial level to today. And why should we limit then this number 2 degrees Celsius? Why 2 degrees? Why not 3 degrees? Why not 4 degrees? If you recall the previous slides, it is well known that, or it has been more confirmed that, if the atmospheric CO2 concentration increases by 2 times, the Earth will warm up something like between 2 degrees Celsius, and some predict to almost 4.5 degrees Celsius. How much warming the humans could safely tolerate is really very complex bioscience. It's not linear. But the 2 degrees Celsius limit was endorsed by a council of German scientists who were basically advised to the then environmental minister of Germany, Angela Merkel, that there is some relation between atmospheric temperature and the survivability of the Earth with regard to how much temperature the biodiversity can tolerate. And then they could convince that 2 degrees Celsius was a good number. For example, very simple way, it was explained. For example, the standard, or I would say normal human body temperature is 98 degree Fahrenheit. If it is 99 degree Fahrenheit, we say it's okay. But if it goes to 2 degree, 100 degree Fahrenheit, we say it's unbearable. Okay, then we declare it is a real fever and we need treatment. 100 degrees is not bearable. Similar relationship was put it that with regard to the survivability of the biodiversity, what is the temperature the ambient can tolerate? So initially the 2 degrees Celsius was considered by arbitrary. Many critics really grumbled with that. But with time, almost all scientists, they said that 2 degrees Celsius is a good number with regard to consideration of sea level rise, risk of crop failure, and so on and so forth. And by 2009, almost every government endorsed the 2 degrees Celsius limit. And this is a nice report from IPCC to 2021. If the ambient temperature rises from 1.4 to 4 degrees Celsius, what happens? What is the impact? If it rises by 3 times, then if you look at the global average annual precipitation rate, it's going to increase by 3.5 times. And the sea level could increase by 2 times. The worst is with regard to the sea level rise. If the sea level rise, the most important, the Arctic ice melts out. then there is much more CO2 which is under the ice than what is in the environment. If they come out because of the ice melting, then that itself can go there on our condition. So now the question is how much the CO2 the environment is going to bear? What is the limit with regard to temperature rise? And for that, when should we give a break? That CO2 is no more tolerable. It's really good analysis has been done with regard to that. For example, if we add 400 to 500 gigatons of CO2 to the environment, with 50 to 67 probability, it can be more or less confirmed that the Earth's temperature could rise to like 1.5 degrees Celsius. Okay, it's below 2 degrees Celsius. Suppose we want to limit to 1.5 degrees Celsius, we cannot increase the CO2 budget more than 500 gigatons CO2. And today we are emitting 60 tons gigaton of CO2 per year. That means how much time we are left with? It's hardly 8 to 10 years. If we want to limit the Earth's temperature below 1.5 degrees Celsius, we friends are very clear that we have only 8 to 10 years with the existing rate of CO2 emission. And if we want to limit to 2 degrees Celsius, then we have hardly 20 years. Maximum budget is 1150 to 1350 CO2, gigaton of CO2. That gives us leverage of 2 decades, 20 years. And the right side graph shows that if we give a break today on the CO2 emission, what will happen to end of this century with regard to the amount of the CO2 emissions and with regard to the atmospheric temperature rise. So these concerns have been felt worldwide. Everyone knows about that. And by 2017, 5 years back, in the United States, to produce 1 unit of electricity, it was emitting something like 500 grams of CO2. Believe it or not, 1 unit of electricity to produce almost half kg CO2 is emitted. Okay. China was emitting close to 700 grams of CO2. United Kingdom 350. France was relatively lower because France produces almost 2/3 of electricity from nuclear. The International Energy Agency predicts that if we want to limit the 2 degrees Celsius, okay, by 2050, what should be the CO2 target? 500 grams of CO2 has to be reduced to something like 10 grams of CO2 per year. Not per year, per unit of electricity. That means 50 times you have to reduce. And the MIT study shows that if you want a deep decarbonization of the energy sector, 11 is not a good number. To produce 1 unit of electricity, max to max, only 1 gram of CO2 emission is allowed. So what is the Indian strategy to meet this Paris Agreement we signed a few years back? So I'm not going in detail to what we signed. Suppose we have to implement the Paris Agreement today. How much CO2 we have to reduce? And today in India, to produce, we emit something like 612 million tons of CO2. That's what I'm saying by the 2030 CO2 levels. That has to go down to something like 400 million tons of CO2 in terms of emission. And that will require to restrict the coal power to below 300 terawatt hour per annum. How much we are producing today? Total energy today we are producing 10,000 terawatt hour per annum. If we want to just comply the Paris Agreement, 10,000 terawatt hour per annum has to be really reduced to 300 terawatt hour per annum from coal alone. Coal is producing 44% of the total energy. Now, the expert says this is not sufficient if we want to achieve the 2 degrees Celsius limit. We have to be going for an aggressive model, similar to that I showed in the last slide, that 1 unit of electricity, we should not go more than 15 grams of CO2. In that case, 300 terawatt hour per annum is not enough. It has to be reduced to below 25 terawatt hour per annum. Okay. So out of 10,000 terawatt hour per annum, which we produce today, primarily from carbon-based sources, almost nothing has to come from carbon-based sources. If we just have to comply the Paris Agreement in a, I'll say, aggressive model. And in the COP26, we also declared 5 nectar points. And the last one is most important. By 2070, we'll be going for net zero. And what is net zero means? If we talk about the atmosphere as a big tank, and that is filled with the global emissions, each year we pump in so much greenhouse gases. In net zero, whatever greenhouse gases we pump into that, we have to remove that. There is no net accumulation. So then only is it possible to meet the 1.5 degrees Celsius or 2 degrees Celsius, whatever we want to comply. And how to accomplish that? The IEA has given set guidelines that how to accomplish the net zero conditions for India. And primarily, if you see that large fraction of the energy has to be produced from hydrogen-based sources, not from hydrogen alone. It has to be produced from green or clean hydrogen-based sources. Not that we burn CO2 or burn oil or burn gas and produce hydrogen. That is not allowed. It has to be produced from clean sources. And 85% buildings also have to run from the low carbon or also that zero carbon sources. 70% of electricity globally has to be from solar PV. Renewables have to run 90% of total electricity generation. Even similar thing also with regard to the domestic consumption. And most important, 7.6 gigaton of CO2, which we have already emitted, has to be removed from the atmosphere. And that will require almost every sector to run by electricity. Because agriculture, industry, our domestic applications, which today are run by coal, oil, and gas, has to run from electricity produced by clean sources, except the transport sector and also some part of the industry, which is also recommended to run on green hydrogen, or they can be run also partly from carbon-based sources. If we don't comply, what will happen to India, also the economic sector? If we don't comply to the greenhouse gas emissions or restrictions, it is also predicted by the World Bank, per year we will be losing almost 7 lakh crores of rupees per year, primarily because the effects due to greenhouse gases by floods, emerging regulations, emission caps, and so on. And if you comply, almost 3 lakh crores of opportunities are there in India. Now, the biggest dilemma. This is my heart of the graph, which I say, the biggest energy dilemma. Is it possible to produce so much clean energy by India? Today, we produce 10,000, and as I said, by mid of this century, suppose we target to produce 20,000 by business as usual model, or 50,000 terawatt hour by aggressive model to have a lifestyle to that of the Western world. Is it possible by clean energy sources, for example, renewable alone? Okay, this is the biggest question. Let us look at what nature has given us and how much is feasible. Only 2 numbers, please remember. Today we produce 10,000 terawatt hour per year, total energy we consume. And by end of this, or mid of this century, how much is feasible from clean energy sources? What is the maximum solar potential for India? The MNRE has predicted that only close to 1,630 terawatt hour per annum is feasible for India, considering 3% of its wasteland, if that will be covered by the solar. It itself is a big number, but that is the maximum solar potential for India. NITI Aayog, the policy body, has also estimated little higher, almost 2040 terawatt hour per year. Professor Sukhatme has done many calculations considering 5%, 10%, 15% of the wasteland to be covered by the solar PV. And according to all these calculations, if I have just summarized, suppose by 2050, storage technology is fully available and there are no losses, anything, 10% itself is a big number. Barren land is cultivated, fully utilized or covered by solar PV, max to max 2000 terawatt hour per year we can get from solar energy alone. Now look at wind, hydro, and bio. If I add all together, whether you are able to see the slides because something is covered by the other and all. So my total calculation is that total we can get close to 4000 terawatt hour per year. Today we produce 10,000 terawatt hour per year. If we want to convert this everything to come from clean energy sources, from renewable alone, we can get only 4,000 terawatt hour per year. So that is a big difference between 10,000 and 4,000. So where will we get the balance of 6,000 terawatt hour per year? Suppose we want to decarbonize this energy sector and 6,000 terawatt hour per year, if we convert to a clean energy sources with a high plant load factor, it gives to 750 to 800 gigawatt electric plant. 750 to 800, please remember this number. So much of electricity to be produced from other sources apart from full potential of renewables like solar, wind, or biomass, and so on. So much of electricity or energy has to be produced from another source of clean source. And what do we foresee with electricity supply from renewables? We all know that renewables are available when the sun shines, wind blows, daytime it is good, nighttime it bad, monsoon are not available, summer it is good, and so on. And because of this regime, their capacity factor is only 20 to 30%. Life of the plant is small. Today, solar PV runs 20 to 30 years max to max and needs replacement, huge waste generation, management of the waste, and so on. Most important, they are all imported. And once they are all imported, what will happen to employment opportunities? If we stop the carbon-based sources, today, coal, oil, and gas are one of the largest employment providers for India. Once we close them, there will be millions who are going to be unemployed. Who is going to employ that? Is itself a big question. The employment opportunities of the green sources of energy sources, vis-a-vis, if we close the carbon-based sources, is a big, I will say that, challenge for India in the next future. What about nuclear power? Excellent base load. It is available 24 hours a day, around the year. So it is an alternate to coal, oil, and gas. It has a plant load factor close to 90%, much higher than any other energy sources. It's not like it's not like solar, wind, or something. Is it the right side? I saw it many times to see that suppose we are eating a cake, the base is basically nuclear, coal, or gas, and the top, which we say that like icing, is basically the renewables similar to solar, wind. This is a very interesting table. Nuclear, as I say, its energy density is very high. Capacity factor is very large, 90%, as compared to solar, it's only 20%. Because energy density is high, to produce 1 megawatt of electricity, we need less than an acre, as compared to renewables, which require 7 to 10 acres of land. Life of a nuclear plant today is 60 years. Renewables is hardly 20 to 25 years. And this technology is well proven for operating for last 60 years. On right side graph is a table if you see. Suppose we build a 100 megawatt electric plant today and is operating 24 hours. So maximum how much energy it can give is 2,400 megawatt hour. Okay. And if we put 100 megawatt electric nuclear power plant, we produce something like 2,167 megawatt hour energy we can get in a day. Coal 1,530, natural gas only less than 50%, 1,220. Hydroelectricity close to 1,000. Concentrating solar is only 792 megawatt hour. Wind 480, and the solar PV, because its capacity factor is very small, is only 360 to 456 megawatt hour per day. That means if I build a 100 megawatt nuclear plant, I sell electricity almost 5 times of that of the solar PV per day. Look at the comparison of the greenhouse gas emission, the grams of CO2 to produce one electricity. As I said, to produce 1 unit of electricity, coal gives something like 820 grams of CO2 it produces. The biomass 740 grams of CO2, natural gas almost 500, biomass 230, solar PV 48 grams of CO2 per unit of electricity, and nuclear is very small, only 12 grams of CO2 it emits per unit of electricity. And this is the graph which I said we all have to worry about. Because of the greenhouse gas emissions and government not permitting the carbon-based plants, the coal-based plants to operate beyond their life, then they are retiring. And you believe it or not, they are retiring very fast. The bottommost table shows that how fast the coal-based plants, which are the drivers of electricity today, for India I am saying, they are retiring. And the right side graph shows that by 2050, most of them will be off the grid. No electricity will be produced by coal-based plants by mid of this century, assuming their design life of 30 years is over and government doesn't give any further extension to limit the CO2 emissions. Okay, so these two numbers, please remember, by mid of the century, almost all coal plants will be off the grid and almost 200 gigawatt electricity, which is the best load to the grid, will be off the grid. And this table shows that by 2017, almost out of the 228 have already retired. This is the report from the Central Electricity Authority. And this retirement are going on or continuing. And if you look at the year-wise capacity addition the last few years, now from 1960 until now, most of these coal plants are small, less than 250 megawatt. So there is a question that balance of plant of these small size coal plants can be utilized to build the small nuclear reactors in that place. And where they are located, these coal-based plants are located in the regions where the coal plants are there. It's easy to take the coal and burn that and produce electricity. And the rightmost I have put the seismic regions where the coal plants are located. Believe it or not, there is a very good thing in the sense that most of these coal plants in India are located in zone 2, and a few are located in zone 3. Hence, they can be replaced because the seismic zone 5 is only not allowed to build a nuclear power plant. Zone 2, 3, and to some extent also, to good extent, zone 4 can be utilized to build nuclear power plants. Hence, I believe that these retired coal plants can be utilized or can be replaced by nuclear. So, this is my question again to the audience. What I asked that 220 gigawatt electricity from the coal are going to retire in the next 30 years. And if they retire, what is going to replace? It's a big question, but I have come here with some solution. Let's look at nuclear power. I have spoken many good things about nuclear power. Today, for India, we have 22 nuclear reactors operating. They produce close to 7 gigawatt electric, 7,000 megawatt electric, primarily from PSWRs, 2 imported BWRs, and 2 imported Russian PVRs. And 9 units are under construction, and 12 projects also approved. And if we go very aggressively, then I say that very aggressively, I'm not going very detailed into that. Then by mid of this century, 2050, 66 nuclear power plants, they may produce close to 50,000 megawatt electric possible by these conventional nuclear plants. Almost 50,000 megawatt electric. And if I convert to the energy, it's very small, only 400 terawatt hour per year. I said in my previous slide, there is a deficiency of 6,000 terawatt hour per year from clean energy sources to come. And if we go very aggressively with nuclear, with the current, I would say that path, we can produce only 400. And that itself is a very big gap, what we have to target and what is feasible. So it is a big difference from the requirement of 6,000 terawatt hour, and what we can produce is only 400 terawatt hour per year from nuclear. This is only if we target only 10,000 terawatt hour. What about aggressive model? If we want to have a quality of life of Western world, I said we should target 50,000 terawatt hour per year, or if we go in the current growth rate, 20,000 terawatt hour per year. That itself is a big question. Probably it may not be feasible to produce 20,000 or 50,000 terawatt hour per year from clean sources. This is my thinking. So what is the solution? Let us look at why current nuclear technologies cannot be so aggressively going on. What is the problem? One thing is that India, if you look at the rightmost graph, we are a small country, a huge population. We are the largest population dense country in the world. Even if you compare other countries like China, Indonesia, US, and France, and this population density is keep on rising. And that is also, if you put a conventional nuclear plant, there are many zoning criteria. These are called regulatory criteria for radioactivity issues. In case of accident, we need an exclusion zone of 1 kilometer of a nuclear site or nuclear plant, followed by emergency planning zone of 16 kilometers, radiation surveillance zone of 33 kilometers, and so on, to meet those criteria if you want to build a large nuclear plant. Suppose we have to have a distance of 33 kilometers or 16 kilometers around a plant, and we want to build several thousand nuclear plants in the country. There will not be any site, no land available for the population to live. That is one of the biggest problems that India is going to see in the next future. We don't have the leverages of the countries like United States, Canada, even China or Russia. We don't have. We have a small land, large population. With the current project cost, construction delays, this is from the MIT studies, to build one large site, for example, a Russian reactor, which we import, the size of the reactor is 1,000 megawatt. And to build that plant, we need something like 25,000 crores. It's a huge investment, and it takes almost 10 years to construct. The interest during construction itself is a huge number. And that is all because this is a non-modular in design. And all these things are to cost. And because of this large project cost, construction delays, many investors don't like to invest. And safety issues, especially after Fukushima, and there were issues of core melt accidents in nuclear reactors. And of course, mitigation strategies like core casters, hydrogen mitigation devices, venting systems are all in place, but they all add complexity, cost, and most important, public fear against nuclear power. Hence, to satisfy the public, it is important that if I build a nuclear plant, the public can live safely around it. There should not be any concern. That means no impact in public domain has to be a really design feature. And let's look at small modular nuclear reactor. can they bring some solution towards this? Yes, the SMR or the small modular reactors are basically small size reactors. Capacity is only up to 300 megawatt electric, and they are targeted to produce large amount of low carbon electricity, base load driver to the grid, and also really green energy supply for producing not only hydrogen for transport devices, also for desalination, district heating, electricity for remote applications, locations, and defense applications, and so on. Small because their size is small, modular because it's like a refrigerator, all components are inside the reactor. There is nothing outside the reactor. So this, because it's a modular reactor, all components like the steam generating system, the pressurizing system, the pump, we'll see afterwards, they're all inside the reactor. This can be factory built as a refrigerator, for example. You just buy from the factory, plug it, and start producing electricity. And small is not new, as you know. Initially, the world's, you look at the history of nuclear power, the generation one reactors were really small, less than 100, I would say 200 megawatt electric size. And they were primarily developed for submarine applications, for strategic applications. Time has come to relook at those designs and how fast they can be deployed. What is the international scenario today? Today, more than 70 of these designs are going on in the nuclear by the nuclear technology holders, primarily by United States, Russia, some from Canada, and also Korea, South Korea, even United Kingdom, Japan, and large fraction or a large variants are from China also. So 70 of these designs are going on by nuclear technology holders, I'd say, around the world. And they can be categorized in 4 categories. Water-cooled, some are land-based, water-cooled, marine-based, high-temperature gas-cooled, even sodium-cooled fast reactors, molten salt-based reactors. These SMRs also, some are targeted for near-term deployment, and some are targeted to come in the, as the far phase, they're called long-term deployment. The water-cooled SMRs are targeted for near-term deployment because this technology is mature, more than 6 decades old. Manufacturing technology already exists, materials well proven, rich operating experience, design life safety well proven, understood, licensing criteria are well known, established. On the other hand, the high temperature reactors, molten salt reactors are considered far-phased because it will take time to prove the design, materials have to be established, regulatory issues have to be resolved, and the economic benefit or the commercial deployment will take time. Amongst the water-cooled reactors, there are 2 variants. One is the block type, if you see left one, another is the integral, the right one. In the block type, the steam generator, pump, everything is directly welded to the pressure vessel of the reactor. Okay, they're directly welded. So there are no pipes in the system. On the other hand, in the integral, inside the reactor itself, the pump exists. Inside the reactor, the steam generator exists. The pressurizer exists. If you look at the right side reactor, it's like a refrigerator which you buy from the shop. It itself is having the pump. Itself is having the reactor core with the fuel. Then the pressurizer, the steam generating system. Only the steam generating system is connected to turbine for producing electricity. And in the right side, one, if you see, there are no pipes involved. So there is no question of any loss of coolant accident. So the safety of these reactors are extremely good. There is no question of any accident occurring in the integral type small modular reactors. And major milestone in history, I'll say that in SMR development has achieved recently in 2020. The Russians were the first in the world to build 2 units of 35 megawatt electrics to produce 70 megawatt electric. Is called Russia's academic Lomonosov, the world's first floating nuclear power plant. And this has already operated commercial operation in May 2020. And this leftmost is called the CARAM, which is an integral PWR. It's under construction in Argentina. New scale is developed by America, is an advanced stage of United States licensing. This is also primarily targeted to replace many vacated coal plants. Around the world, they have already signed agreements with many East European countries and also Asian nations. The rightmost one is the Korean one, which is called SMART, is already licensed and is targeted to be deployed first in UAE with a consortium. So how these small reactors, small modular reactors address the issues of current nuclear safety? And the most important, as I said, they are designed with a trademark of no impact in public domain. In the sense, the reactor size is small, the radioactivity inventory is small, and they are all cooled by passive means, in the sense that if any accident occurs, it never goes to a core degradation condition. And the result of which the activity released beyond the nuclear reactor plant boundary never exceeds any allowable dose limit. So there is no question of public evacuation, no question of public concern. It is so said that it is also claimed like walk away safe reactor, in the sense any accident occurs, the operator can forget the reactor, he can go to his house and sleep, and still it is safe on its own. That's why it's trademark of no impact in public domain, most important feature of these small modular reactors. In fact, we have done some first-hand calculation of these reactors. These reactors are really submerged in a water pool, and the containment itself is a steel containment which can be cooled indefinitely by air. And what we have seen, in case of any accident, the maximum temperature the fuel-clad sees is only a 750 degrees Celsius if it's a 100 megawatt electric size. As a result of which, forget about core melt, even hydrogen production by metal water reaction will not happen. It is cooled indefinitely by air. And look at the difference between the right side, it's a conventional reactor, and the left one is an integral reactor. Integral reactor means everything is put inside this pressure vessel. So this integral reactor, as I said, it houses the entire nuclear steam supply system, the reactor coolant channel, the steam generator, the pressurizer, fuel, everything as a single product. This is built in the factory, transported by the road in a truck, and assembled in the site. So there is no question of any site work or much site work involved. Because the size of this reactor is small, that's a 100 megawatt electric, the investment is small. It's hardly, let's say, 2,000 crores, unlike 30,000 crores for a large size reactor. And so many small investors will be tempted to invest in the small reactors. And because it's factory assembled, the construction period is very small. It is expected into 2 to 3 years, one reactor can be constructed or connected to the grid. So in 2 to 3 years, the investor will start getting the return. So many investors will be investing in this type of reactors. And there was a big debate because a small reactor, the cost per megawatt could be very large as compared to the large size reactor because of the economics of the size. Then there were a lot of calculations worldwide, and it is found that because we are going to speak about several thousands of these reactors, so because of the multiple units which are going to be factory built, and these are modular in construction, as well as they are going to be located, they are factory built, modular in nature, and the construction schedule is very small, 2 to 3 years as compared to 10 years, 8 to 10 years for large reactor. The economics of scale will not matter. In fact, their cost is expected to be comparable to a large reactor. The recent UK study shows that if we build, United States study shows that if we build 4 units of such SMR, the cost is between 5 to 6 rupees. And then it's quite comparable to that of a large reactor unit. And most important for India, as I said in my last slides, that if the retired coal plants or the coal plants which are retiring, there will be large unemployment generation. If we build several thousands of these reactors, it will, with the Make in India, this is going to create hundreds of employment opportunities for manufacturing, service sectors, and that will reduce the unemployment problem for India. And what is the Indian domestic manufacturing capability today? This also we have explored. The size of the SMR is selected based on the domestic manufacturing capability. If we see our forging limitation for India, the largest what we can forge is maximum 200 tons, which gives to a 60 tons finished product. And if we go by a 100 megawatt electric size plant, the reactor pressure vessel is almost 3 meters, and the corresponding thickness of the pressure vessel, this can be directly forced without any import requirement. So the manufacturing, domestic manufacturing possibility 100% exists for this size of the reactor. And then our road itself can transport this single reactor units up to 500 tons, which is also possible by Indian road condition by truck. And because, as I said, the size of the reactor is small, we have explored that in case of an accident, the decay heat can be completely removed by passive means to practically eliminate or melt accident conditions. The dose limits also have been evaluated, and what we find that if the size of the reactor is very small, 100 megawatt electric, with all passive systems in place, then the dose limit at the site boundary can be less than 10 millisievert. And if the dose is less than 10 millisievert, there is no question of any, I'll say that, intervention in the public life, that if there is an accident. And in the normal exclusion zone of 1 millisievert per year can be easily maintained at the site boundary. In view of this, the dose criteria for this size of the SMR is easily feasible for Indian, I'll say that, retired coal plants. And we have already worked out the size of this SMR as a basic design study. And this looks like I don't know whether you are able to see the right side view. I have made a good, I think, yeah. So this is basically a natural circulation based small modular reactor, and the reactor core is put at the bottom. The hot water goes to the top, and the pressurizer is sitting at the top. As it goes through the steam generator, the steam generator is basically once through steam generator, it takes away the heat, and the steam goes to turbine producing the electricity. There is no pump. The cold water, after the heat is removed by the steam generator, enters into the reactor core bottom. This way, the fission heat is removed. On the right hand side also shows the similar behavior for the primary side and secondary side. Then we have also find out what is the size of the footprint required to place about 4 into 100 units, that is 400 megawatt electric of this size reactor. We find that it's roughly like 250 meter by 250 meter. Then what I did, we tried to put all our all our vacating or to be vacated coal size plants with this type of SMR. We took a 3,760 megawatt electric coal-fired thermal power station as an example. This size, this thermal power plant, it occupies 10 kilometers square area without ash pond, and if you consider ash pond, it's another 23 kilometers square area. If we put a conventional reactor, with 500 megawatt electric, it will be occupying only 0.8 kilometers square area in place of 10 kilometers square area. And if we put consider the exclusion zone, it's only 3 kilometers square area will occupy. And if the same area, 23 kilometers square, is given for solar, max to max we produce 720 megawatt electric. And same area is given for wind, is only 568 megawatt electric. So you remember, initially the coal plant was producing 3,760. If this land is given for solar, only 720 megawatt electric. Wind is much smaller. Then we mapped the land with SMR. What we find that in the same land, we can produce 3,200 megawatt electric from SMR. And if we consider also in the extrusion zone, we put the solar PV, together we can produce 3,930 megawatt of electric. It is much higher than what coal was earlier producing. Then we try to map also other sites. For example, in Odisha Talcher, there is a thermal power station. Today it has already, I would say that abandoned. This site has been abandoned. Earlier it was producing 460 megawatt electric. In the same size, if we put the SMRs, it will be producing 600 megawatt electric. In Guru Gobind, a Roper thermal power station, existing thermal power produces something like 1260 megawatt, and we put the SMR in that plant, it will produce very large number, almost 15 gigawatt, 15,000 megawatt can be produced from SMR. In Faraka thermal power station, today it produces 2,100 megawatt, and if we put the SMR in that site, it will be producing something like 2,000 megawatt. All these studies have been done in collaboration with NIAS, Bangalore. Then we started to map some of the captive power plants at Nalco, because in India, almost 30% of the electricity is consumed by the captive power plants. So one of the captive power plant at Nalco, we tried to map it also. So in Nalco, it produces almost 1,200 megawatt from coal, which is used for smelters. So this is the map of the existing coal power plant. And we try to put the SMRs. So what we find that we can easily produce 3 into 400, that is 200 megawatt electric in the same size. And if we occupy a little bit more area in the same place, even we can go for 2,000 more 400 megawatt electric. Then in Uppur thermal power project, in existing, there is 2 into 800 megawatt coal thermal power project. This was really allotted, but this has not been built. Then what we did, we tried to map it using the thermal, using the SMR. We can produce almost 12,800 megawatt from almost 12.8 gigawatt. So we try to speak it like it can be made as a SMR park for India, a huge small modular reactor park for India. Similarly, in Manuguru, no, this is not Manuguru, this is in Kothagudem. There is a brownfield site. It is 13 modules of SMRs has been, we have proposed, and they can produce something like that 5,200 megawatt. Similarly, in Badarapur thermal power station, 5 modules can produce 2,000 megawatt in that site. So what is the advantage? Advantage of replacing the vacated coal plants are the follows. One is land acquisition for the plant. There is no question of further land acquisition, because already in the name of the state government or in the name of the NTPC or other coal plant owners. So this can be easily replaced by the vacated coal. No further land acquisition. Water body is existing, because almost 60% of the thermal energy in the coal power plant is diffused as the ultimate heat to the water body. So they are already available. Site survey is available. Transport facility, all vacated coal plants are well connected by rail and road. Decommissioning of boiler turbine, many places has been done. If not, they can be also further utilized. Trained manpower, especially for coal fire plant, exists, and they are already unemployed. They can be used to be utilized for the balance of plant. Need not be for the nuclear, but if they're trained also, they can be used even for the nuclear island. Township already exists, so no further construction. Local facility already exists. Sewage treatment plant already exists. So all these things will not only significantly reduce the timeline, but also I would say that utilize the existing infrastructure by reduction in the cost. Another major objective, as I said, is the green hydrogen production for transport and Indian industry. And when this retired or vacated coal plants to be replaced by SMRs, and whenever there is lesser demand of electricity, for example, in the night, could be lesser demand of electricity, these SMRs can be utilized for green hydrogen production. Almost for megawatt of electricity, 480 kg of hydrogen can be generated, as you all know probably, using standard low temperature electricity. And if you go for high temperature reactors, almost 630 kg of hydrogen can be generated. So SMRs, apart from electricity production, can be utilized for hydrogen production also. Most important for India is providing clean drinking water. Believe it or not, we are a small country, population is growing year and by year, 1.4 billion. Today, another 30 crore waiting to join us. And when we'll have 1.7 crore, 1.7 billion people in this country, is predicted by UN already that we could be one of the water scarce country in the world because of the depletion of the water level and larger consumption from the industry itself. So the agriculture, industry, and human consumption will require much clean drinking water, which will be difficult to get because rain God gives the same amount of water irrespective of the population rise. It doesn't increase. From 1960 to 2050, the amount of water which rain God gives is constant. But we have increased the population from 36 crore to 1950 to almost 170 crore to 2050. So I believe that several of these SMRs can be constructed close to the Indian coast because they will not be requiring any emergency planning or other requirements. And these SMRs can be utilized for desalination. And typically 4 megawatt, 6,000 meter cube per day of clean water can be produced by SMRs and which can be utilized for meeting the clean water demand to a large extent. So with this, I conclude my presentation and I thank the TIFR for giving me this opportunity to speak. Special thanks to Professor Satyanarayan, Professor Datta for their kind invitation and giving me this opportunity to speak before this audience. Thanks a lot.
Thank you very much, Dr. Arun Nayak. I invite back again Professor Vivek Datta.
No, maybe Satya, you could conduct the question answer session.
Okay.
I have a question myself, but anyway,
you yourself have a question. Please go ahead, sir.
Okay. So thank you, Dr. Nayak, for a very nice lecture, very comprehensive in terms of what we could do, what are the problems and so on. I'd like to ask the following. How much is the investment that would be required if you want to get to this figure of replacing or maybe even enhancing the power capacity of the coal plants that you wish to populate these small reactors?
See, look at actually, for example, I'm giving one example, NTPC. NTPC today holds almost 70 to 80,000 megawatt electric or 80 gigawatt electric coal plants out of the 220 gigawatt electric thermal power plants. So these companies like NTPC or other state government, I don't know who are the other companies, but primarily NTPC and other thermal power companies, they will be now probably have to be inducted into the deployment of the SMRs because it will be difficult for government to invest because it's a huge investment will be required. Suppose we talk about 200 gigawatt electric by 2050, for example, I'm just giving a number. And my estimate is 100 megawatt electric plant will require something like 2,000 crores. So 1,000 megawatt, that is 1 gigawatt, will be requiring something like 20,000 crores. So 20,000 crores into 200 gigawatt will be a huge number of money which will be required. But that will not be happening immediately. That has to happen gradually, because in this there is one advantage in the small modular reactor, unlike the large reactor. You invest for 5 or 10, and that return you can get and invest for another 10. And this many units can happen in parallel. And major thing that many private industries will invest in this case. So I'm not naming an industry today, but many private industries, manufacturing industries, because it will create a huge employment opportunity in India, huge manufacturing and service sectors. So I believe it will create a financial boom, economic boom, employment boom for this country.
Okay, one small question. What about the fuel? Would it be enriched uranium or would it be heavy water based reactors?
No, the one I showed is a conventional PWR based reactor.
Okay, light
So
water.
the enrichment is 4 to 5% of that level.
Okay.
Yeah.
So this we would have to again depend on our own enrichment facilities. Maybe we
Yes,
want to
it
enhance
has
them.
to happen.
It has to
Yes.
enhance.
Yes, yes.
Okay.
And I believe this is my personal philosophy also. The 3-stage program has to continue also in parallel. That water-based SMRs, whatever fuel they produce, I've said that the spent fuel can be reprocessed to produce plutonium, which the fast breeder reactors can be tomorrow. I'll say that they must design small modular fast reactors, small modular thorium-based 3rd-stage reactors. So then they don't have to go to public, put the reactors outside the public domain. They can be put inside the public domain. So the 3-stage program can run, because I said we require 800 to 1,000 gigawatt electric from nuclear in the next few years. So only water cooled cannot give. You have to go for sodium and thermal reactor. Thorium-based reactors also. So this has to.
Thank you.
Okay.
So let me see if there are any more questions.
Yes, sir. I'll take. So, Acharya.
Yes.
Yeah.
Please.
Yes. Yeah. Thank you for a very nice talk. I am just curious to see whether any mini or micro SMS or SMRs are possible, in the sense, if such a thing is possible, then each housing complex or big house, because it doesn't take much space to house it, no? So therefore, each small city or this they could have some of their unit and get the power required for them. Okay.
I think what you said, that is the next vision, definitely. See, right now we are talking about small modular reactor. Next will definitely the technology will go to micro modular reactor, and that will be inside a city. In fact, in United States, they're targeting the same. So for that, the fuel there, I think designing will be different than the conventional nuclear fuel. So that will take some time, let's say another 20, 30 years. Then the micro modular reactor will come into picture, definitely.
Yeah. Also, will that, because of the if the safety improves, will there be a possibility of using it, that micro SMRs in the transportation sector?
Yes.
Like each ship can have its own.
Yes, yes. Ship already, ship, I give the example, Russians have already doing that.
Okay.
China is already going to deploy. China, Korea in deployment stage, yes.
Okay. Yeah. That's all right. Yeah. Thank you. It was a very nice talk. Yeah.
Thank you.
Thank you. Acharya. So Sandeep Ghosh has a question. Sandeep, do you have a question? We can't hear you.
Maybe he could type his question or something in the chat, and then you can articulate it.
Sandeep, if you want, you can type your question in the chat. Okay. He actually typed one. He says, maybe I missed it, but what about the challenge for waste management?
Okay, the waste, there is we are not talking about a nuclear waste generation, because we have to go for a closed fuel cycle, definitely. Because I said we need large power, not necessarily, not to limit even 200 gigawatt of electricity. So our target is basically to go for a closed fuel cycle. So the whatever this SMRs I presented is from a conventional PWR based fuel. So the spent fuel has to be reprocessed, of course, and the plutonium to be generated has to go for the second stage and then to the third stage. And once we go for closed fuel cycle, the amount of waste generation has to be will be minimized. That is one part. Second part is unlike the PSWRs, or I don't name also PSWRs, but unlike, for example, the waste which do not reprocess. So there is a question of storage and all. There is issues there. But for us, since we are going for a closed fuel cycle, I believe that the waste itself is not a major issue for us. Hello, have I asked?
Yeah, yeah, you said, okay, that's what I want to take one question from YouTube. This is Abhinav Chaudhary. This is, of course, it's a kind of complementary process energy source. In near future, what is the scope of energy from nuclear fusion in India?
Nuclear fusion definitely is will be the blessing for this global energy, I would say that crisis because of global warming. But technology will take time. I think, in my opinion, by 2050, if this is proven, then another 50 years it will take for commercial deployment. So let us say that is the technology for 2100 and beyond. So for this century, the fission-based technology will be definitely the drivers for nuclear. Fusion will take time.
Yeah, any other questions to Dr. Nayak? Okay. I don't see any, so I would like to thank Dr. Nayak for very, very important, on a very important topic, and making a strong case for countries like India in particular, that why it is so important to move towards the small modular reactors. And okay, with this long preface in which he kind of made a strong case for it. And at the same time also looking at various technologies that are somewhat proven and ready to go. And so I hope we will soon have at least start having maybe a model kind of a reactor, and then soon it will be a reality for India, and in a level that it is most suitable for us, and also meeting the projected demands of 2050 and using all the clean forms of energy. What is also important is, or interesting is, besides electrical energy production, but also the spin-offs of hydrogen and other, you can say, spin-offs or byproducts of these reactors are also very equally interesting. And then the way Professor Acharya was mentioning about using even smaller, even micro kind of reactors for transportation, for and other areas is, I think, very, very far-reaching and interesting to look forward to. So once again, would like to thank you, sir, for this is a very, very interesting lecture. And also, I said, would like to thank Professor Datar and also Mr. Prabhakar for reaching out to you and making this talk possible. Thank you very much.
Thank you.
Thank you, Dr. Nayak.
Thank you. Thanks a lot, Dr. Datar.